This maybe is being like.
Welcome to our first recorded recorded lecture for our physics class. I'm going to try to have this not take too long. But I think the easiest way to present the three chapters, chapter 2, chapter 4, and chapter 5, is kind of all at once because they're all related to the same big idea. We talked a little bit about Galileo last week. But before we say more about Galileo, we should talk a little bit about what came first. The prevailing wisdom for hundreds of years was due to Aristotle, or at least Aristotelian thinking. Trying to advance the slide, and all I did was make it down. We can argue that Aristotelian thinking was the seed that grew into the scientific method that we're familiar with. This word classification is really all Aristotle and Aristotle's disciples were doing. They made some observations, which is scientific, but then that's kind of as far as it went. And they hypothesized. At least we know now that what they did was hypothesize. But they declared an explanation for the things that they saw, and that was the end of it. The process was about finding a way to explain what was going on, and then as long as we had a coherent way to talk about it, that was enough. Never mind that it wasn't correct. It was actionable, I suppose, in the sense that, well, it was reliable. Natural motion, according to Aristotelian thinking, relied on the fact that according to its composition, of the four elements, earth, water, air, and fire, each object has a natural place in the universe. Rocks, for example, stones, have their natural place is on the ground. Because, well, I mean, I guess it makes sense to say that. I've never encountered a rock that wasn't sitting on the ground. Like, I don't just find them hanging out in the midair. They're always on the ground. And if I pick one up, if I disturb it somehow from its natural place, once I let go, it falls and returns to its natural place. Smoke, on the other hand, if I light a fire, smoke rises. I very, very rarely, as I'm going about my business, see smoke hanging out on the ground with rocks. It always is floating up. So the Aristotelian thinking is that, well, smoke rises because it is supposed to, because it has that natural, that's what it does. And that rocks fall because that's what rocks do, not because there's anything happening, just because, well, that's what it means to be a rock. Basically, we're making room for up and down. On Earth, everything's up and down. And you say, well, what about people walking around, or horses pulling chariots or something? And say, okay, but we could, I think, I mean, if we're going to be Aristotelian, we could call that violent motion. Motion that's produced by external pushing and pulling. My body's natural sort of state is to sit here until I go and do something. I get up and I walk around, and I use my feet and move. But up and down is all that is naturally allowed, unless you get beyond the earth, because the sun and the moon appear to circle the earth. So outside our sort of experience, once we start talking about suns and moons and stars, all that kind of motion is circular, and all this kind of motion is up and down. Why? I don't know. How true is that? Also, not really sure, but it's enough. It was enough to act on, I suppose, enough to sort of go through life relying on. You know, and it's true. I don't encounter a rock floating in midair. It's just, it doesn't happen. Now, it's not because there's something special about rocks that means that they only exist on the ground. It just means that, well, we know why they're on the ground. Gravity. And we talk about Newton's laws of motion, but it's really Galileo's sort of insight that Newton built on to sort of write down mathematically the laws of motion. It took a few hundred years, but Galileo was able to, with evidence, argue against the hypothesized explanations for why the universe looks like it does from Aristotelian thinking. We talked about the Leaning Tower of Pisa experiment. If we can neglect or otherwise account for, control for the effects of the air, two objects of different weights fall at the same rate. And we talked about what rate that is, and we've done a little bit of work with free fall already. But it was an experiment, and Galileo was able to present evidence. It's not the weight that changes how fast things fall. There's something else going on. Galileo's other insight has to do with this idea that a moving object needs no external push to keep it moving, as long as there's nothing acting to slow it down. Now, this is like opposite to Aristotelian thinking. As far as Aristotle was concerned, the natural state of these physical objects was at rest, because that's how we found them. And it's Galileo's experiment, and he's able to reason from experiment to claim convincingly that a moving object, if nothing happened to it, would continue to move indefinitely. His experiment had to do with rolling a ball down and then up a pair of inclined planes. As the ball rolls down, it speeds up. And we talked a little bit about that experiment already. As it rolls up the second slope, it slows down again. And Galileo noticed that it always got to about the same, if we use, the same downward slope as upward slope, that the ball almost always got very, very close to the height from which he released it. So he changed the second slope, roll it down the same steepness first slope, but then make the second one, the upward slope, shallower. So let me show you what I mean. So instead of just going down and then up, He says, okay, let's go down and then up. And it needed a longer slope for the ball to come to a stop because it was always trying to get back to the height from which it was dropped. And so he started to think, well, what if instead of an upward slope, after I let it slide down, what if it's just flat? It's always going to be trying to get back to the height from which it was dropped, but it can't because the road doesn't go that way. So his sort of leap of reasoning, the ball would continue traveling forever. If it doesn't, Galileo said, well, there must be some extra thing happening to it to slow it down. And I think this idea is related to his ideas about the air, that if we can, if it would occur to us, right, to drop two objects of different weight but equal size, to show that if we control for the air resistance, objects fall at the same rate. That air resistance takes on, it's one of these forces. It's one of the things that happen to a moving object to try to slow it down, to resist that motion, like friction, which we'll talk about in a second. If those things didn't happen, Galileo inferred the object would continue moving forever. And he named this property inertia. We can formally define a force as a push or a pull, and inertia as a property of matter that tries to preserve motion. Whatever the motion is, if it is at rest, then this mass will try to stay at rest. If it is moving, it will try to stay in that state of motion. Whatever its speed, it will try to keep. Whatever its velocity, it will try to keep. And we talked about the difference between speed and velocity last class. The heavier the object is, the harder it is to start a resting object moving. So we say that, well, that object resists changes in its motion more. So if inertia is this property, this tendency that matter has to resist changes in its motion, then mass or weight, which are related, mass does a good job of measuring how much inertia a thing has. Another 100 years or so later, Isaac Newton returns and builds on Galileo's work because a lot of work is being done at the time that Newton is writing in the well, I guess formal mathematics. Newton is involved with that. There's a handful of people working on that, and using that formal mathematics, the mathematics of the rate of things. And we've talked about velocity being the rate of change of location. So in the context of building this mathematical language, Newton writes about the idea of inertia, that every object continues in a state of rest or of uniform speed in a straight line, uniform velocity, in other words. Uniform speed in a straight line, that's the same as uniform velocity, unless acted on by a non-zero net force. All right, so there's a couple things we've got to unpack there. Non-zero, I go, okay, it can't be zero, but the word net has some implications for us, and we'll be talking about those here in a minute. In order to talk about net force, we have to define really what we mean when we talk about vector quantities. And we've talked about vectors a little bit. The difference between speed and velocity is that velocity includes information about the direction. So that if I push a thing one way and somebody else pushes the same thing the other way with an equal push, our intuition says that those two pushes will amount to nothing. That if each push in either direction is equally strong, then the thing won't move at all. And it's vectors and the fact that they care about the direction that allow us to sort of attach some math to that intuition, which is very much correct. Let's represent these directed quantities with arrows drawn to scale according to their amount. The length of the arrow represents the magnitude, the size of the vector, and the direction of the arrow, the direction the arrow points, is the direction of the vector. So for example, two vectors that point in the same direction, the second one is larger. The magnitude of that vector is greater than the magnitude of the first one. When we say net force, we mean the sum total of all forces that act on an object. For example, if two people push or pull on a block, this gray thing here, with 5 Newton pulls, which I guess makes me think that we're going to name the unit of force after Isaac Newton. So this 5N here, that's 5 newtons. If two people pull on that block with forces each of 5 newtons in the same direction, we can add them sort of traditionally and end up with 10 newtons altogether pulling in that direction. But if one person pulls with 5 newtons in one direction and the other person pulls with 5 newtons in the other direction, that's like this situation that I just demoed where two people were pushing in opposite directions with equal forces. Think of it like adding 5 to the right and 5 to the left, and let's call the 5 to the left -5. So we add 5 to the right and -5 to the left, and we end up with 0. And that mathematics matches our intuition that if equal and opposite forces act on a thing, it's not going to go anywhere because nobody's winning. Suppose we don't know before we start how strongly different forces are acting. But here's an example. We've got a string holding up a bag of flour. Two forces act on that bag of flour. There's gravity, it has some weight, and the tension in the string. The string is responsible for holding up the flour. Because if we cut, and we know that, because if we cut the string, the flour falls. So, but for the string being there, the flour would fall. All right, so the string is responsible for holding up the flour. If the flour remains at rest, according to Newton's law that we just talked about, Now, an object at rest stays at rest. An object in motion remains in that motion unless acted on by non-zero net force. So the bag of flour at rest is remaining at rest, which must mean, since we know that there are forces acting, that they have to be adding to zero. They have to cancel out. They are equal and opposite. Just like the two 5-Newton forces in the second part of this figure. We call that equilibrium, when all the forces acting add up to zero so that the motion doesn't change. There could be more than two, as long as all the forces, the sum total, the net force acting on an object or a system is zero. Those two upward forces are the tension in the strings holding up this plank. Those three downward arrows, these three, are the force, the weight, the gravitational force acting on the two painters and the beam that they're standing on. And if we add that all up, hopefully, for the two painters anyway, the sum total should be zero and the whole system stays at rest. Now, when there's a string holding things up, it's easy enough to see, but if I put an object on a surface, the object, this coffee mug, is staying at rest, which must mean that there are, because I know that if I didn't put it here, if I moved it over here, it would fall. So there's something special about the tabletop that keeps the coffee mug in equilibrium. We look for a support force, which is sometimes called a normal force. And the reason for that is that normal is an old word that means perpendicular. The tabletop pushes perpendicular to itself. The floor holds up my chair perpendicular to the floor, which is good because this chair is on wheels. And if it weren't perpendicular, some of it would push me to the side all the time, which would be really annoying. So support force, that's a little bit more, I guess, intuitive. When we say it is a support force, we mean that it's holding something up, it's supporting it. A book on a table compresses atoms in the table, and the compressed atoms produce the support force to hold up the book. So there's an atomic interaction between that coffee mug and the table, by which the table, the atoms in the table, are able to provide a force up equal to the weight of the cup down. When the book pushes down, is in contact with the table pushes back. It's sort of like if the cup is here and not in contact, if there isn't a downward force as a result of contact with the table doesn't push back. There's no reason for it to do that. When the book or the coffee mug pushes down on the table pushes back to stay in equilibrium. Okay, so exactly that. So far, we've talked about one kind of equilibrium. Remaining at rest, static equilibrium. In other words, there is stasis, which is, it's the same root as stationary, not moving. A hockey puck at rest in the middle of the ice rink is in static equilibrium. It's just sitting there. However, that's not the only kind of equilibrium, because Newton's first law that we said a second ago, an object's state of motion remains unchanged, whether it's at rest or in motion with some velocity. Suppose we use our hockey stick to hit the puck. It'll slide on the ice, and if it's sliding at constant speed in a constant direction, its motion isn't changing. And that's a different kind of equilibrium. That's equilibrium where something's in motion. So we can call it dynamic equilibrium. It's not standing still, it's not stationary, but it is still equilibrium because the motion isn't changing. Whatever motion there is continuing. Does the motion change? Not the same question as does its location change? A thing moving at steady speed in the same direction is in equilibrium just as much as a thing that is remaining at rest. Even though, yes, that moving thing is changing location, the motion that it is experiencing is constant, isn't changing. And so, equilibrium. Sorry about the formatting there. That the Earth is moving, circling the sun in direct contradiction to Aristotelian thinking. And I guess that's the moral of this story, that Aristotle and folks following in that tradition had some good ideas, but were wrong about a lot of things. So Copernicus makes some observations and decides, yeah, actually, maybe not. Maybe the Earth is moving around the sun. And people argued with that idea. And their attempt at evidence, if the Earth were moving, how could a bird swoop from a branch to catch a worm? By the time it got there, the Earth would have moved. And now that we have this idea of inertia, if the Earth is already moving, according to Copernicus, when at the instant the bird leaves the branch, it's already moving at the same in the same way that the Earth was, because it was sitting on the branch, which is connected to the Earth just an instant ago. There's no reason for its motion to be any different than the motion of the rest of the things around it in our, earthbound viewpoint. So is the worm, so is the ground, so is the tree, and so are we if the Earth is moving. But that doesn't mean that in our perspective, the bird can't move from branch to ground, get the worm, and go back, all while the whole Earth is moving through space. Because we now have this idea of inertia, we can refute these folks' counter argument. Even if the Earth was moving, it's okay because that bird has inertia associated with its earthly motion. So we can happily allow our observation of the bird swooping down to get the worm. Yeah, but that could just be over top of the Earth's otherwise motion around the sun. Okay, so we have this idea of inertia, and we have Galileo's idea of inertia, and we have Newton's first law, which kind of expresses it in a nice way. Unless acted on by non-zero net force. Now, force, in order for this trick to work, has to be a vector quantity, because 5 newtons this way and 5 newtons that way need to add to 0. Fine. What do we do if there's 5 newtons east together with 5 newtons north? Those don't directly oppose each other. If I push something up and then I push it to the side, it ends up and to the side. So what if 2 people push at the same time, one pushing up and one pushing to the side? Do we expect the thing to move up and to the side? Diagonally, kind of? Maybe. But in order to be precise about these forces, these vectors that are acting, because we need to have some math if we're going to add them all up so that we can determine whether equilibrium is, achieved. We've got to talk a little bit more about vectors. We've said already that a vector quantity has a magnitude and a direction. Velocity is our first example of a vector quantity. But since we define velocity, we also have acceleration, and now we also have force. We've also talked about quantities that are not vectors, that do not have direction. Mass is a good one. Speed is another one that we defined the other day. Volume of, not like turning up the volume of a sound, but the volume of an object, the space that it takes up. The other example that we've talked about so far is time. 4 seconds east doesn't make any sense. Time doesn't have a compass direction. It's just 4 seconds. In order to find the sum, because if we're going to talk about the net force, what we mean is the total, the sum. For vectors, we've already talked about this. For vectors in the same direction, we can add them. For vectors in opposite directions, we end up sort of adding a negative or subtracting. We said 5 and negative 5 add to 0. 2 vectors that don't act parallel or anti-parallel, we have to talk about parallelograms and or right triangles. In this case, I'll be your neighbor. Which of the following are true? All right, what are we looking at? We've got a 30 Newton vector. Let's say that we've got a compass rose here. North points up the screen and east points to the right. So we've got a 30 Newton vector north. At the same time, a 40 Newton vector points east. Now, let me go back a screen. If two vectors are at right angles to each other, we can use the Pythagorean theorem. So if we form a parallelogram, which if those two vectors are perpendicular, that parallelogram we're talking about is actually a rectangle. If it's a parallelogram of any kind or a rectangle, if one side is 30 newtons big, so is the other side. And then what we have is a right triangle. And if we have a right triangle, we can use the Pythagorean theorem. So let's call the resultant, the sum, let's call it R. That's the length of that hypotenuse. And the Pythagorean theorem says that we could find it by R squared equals, well, I guess A squared plus B squared, or yeah, let's just write it that way. One leg is 40 newtons. 40 newtons. The other leg is 30 newtons. Let's square both of those and add the results. So 1600 square newtons, because we do have to square the unit as well, plus 900 square newtons is 2500 square newtons. But then, don't forget, we just talked about R squared. If we want R, we need to take the square root of this whole thing. And if we take the square root, we do get 50 newtons, because we can take the square root of Newton squared and end up just with newtons again. So I think, yes, that's supposed to be a check mark. Okay. Yes, the 50 Newton vector drawn is the result, the sum of the 30 and 40 Newton vectors. Now, what if we thought about the 50 Newton vector to start with? We could, because this equation works two ways. We can find R if we have the two legs, but we could also find the two legs if we had R. We can think about the 30 Newton vector as a piece, a component of the 50 Newton vector. So yeah, I think B is a true statement as well. But if B is true, I think C is also true, because the 40 Newton vector can also be thought of as the other component of the 50 Newton vector. Those two pieces put together yield the 50 Newton vector. So if we're thinking about the 50 newtons, we could sort of break it up into a north and an east according to the direction of the indicated direction of vector R. And what we would end up with is that the north part is 30 newtons and the east part is 40 newtons, according to the shape of the triangle that we would need to break that 50 Newton vector into. So we end up saying D, all of the above are correct. Okay. So, no, not that button. Sorry. My finger has become a pen. I got the slide to advance. Here's another sort of application of this vector idea. Nellie Newton hangs from a rope. Which of the two ropes has the greater tension in it? There are three forces acting on Nellie. Her weight, which is drawn, mg, a tension in the left-hand side of the rope, and a tension in the right-hand side of the rope. Now, hangs from a rope at rest in equilibrium. So the sum of these vectors needs to be 0. The only way that can happen is if the two rope tensions add up, result in a vector that's drawn that is equally long and opposite her weight. I don't know what this was working before. I got to use the pen to write and my, tap to advance. Let me just do it this way for now. Because of the different angles of the two ropes, the tensions will be different. Excuse me. Because she's in equilibrium, the result of the two tensions needs to be as drawn. In order for that result to be the actual vector sum of two vectors, the tension in the two ropes, that are along the two ropes, we only have one choice. In order to draw a parallelogram along with sides along the two ropes, and with diagonal equal in length to her weight, it's got to be this. Equal in length and opposite in direction. There's only one parallelogram that will do that, and it's the one that's drawn in green. In order for that to be the parallelogram, the two vectors we're talking about need to be these two. So we know that the right rope has the greater tension. Velocity is a vector. We were just looking at forces, but that's fine. Velocity is another vector. If at some instant the velocity of a stone is along this vector, up and to the right, we could, if we wanted to, find the vertical and horizontal components of that vector according to that direction. The only way that can be the diagonal of a parallelogram is for this to be the parallelogram. So there is a horizontal component that big and a vertical component that big. Has to be. And this sort of decomposition works for any vector, any directed quantity. Velocity, acceleration, force. Here's an example. Here's Nellie Newton again. She's pulling on the sled. Which component of her force is greater? The horizontal or the vertical? And we can look at the picture. Remember that vectors are drawn to scale according to their magnitude. And since the horizontal component is larger than the vertical one, the horizontal component is greater. Which two other forces act on the sled? They aren't pictured, and there are two that act on the sled. And the key to answering that is that gravity always acts, but that the sled is just moving across the ground. So there must be a support force. The sled and dog have some total weight, some gravity that's acting, and the normal or the support force also acts. So we could draw the weight and the normal force, equal and opposite. We might, why didn't we draw them? Well, they cancel. They cancel each other out. So the only forces that are causing motion of the sled is Nellie pulling. So maybe that's the part we'd like to emphasize in the diagram. Another example. Two forces act on this block of ice. So there's a block of ice sitting on some more ice. If we tilt the ice, this ramp, right? We've got the support force and we've got the weight of the ice. Which force, if any, remains constant? And then you know the answer already because I accidentally advanced too far. Gravity acts on the block of ice no matter what the orientation of the ramp is according to its weight, mg. Now, what is this mg? It's a great question. Hold that thought. We're going to answer it. As the ramp is tilted, how does the normal force change? The support force. Remember that support forces are only in response to the contact with the object that's being supported. The block of ice is in contact with the ramp, and so the ramp responds. How much is the block in contact with the ramp? And remember that support forces, normal forces, are perpendicular to that surface. So here we've got the surface of the ramp, and the normal force is perpendicular to that. In order for that normal force to be a response to the contact from the block of ice, and the block of ice is really only pulled down against the ramp because of gravity, there is a parallelogram here to talk about the gravity, the components of gravity that are along the ramp and normal to it. This normal part that's the part that the ramp is responding to with its support force. The other component, this one, oops, still on highlighter, this one, that's the part that's going to make the block of ice slide down the ramp. As we tilt the ramp, check what happens to the parallelogram. The component that is perpendicular to the ramp has gotten shorter. It used to be this long, but now it's only this long. That one. The component along the ramp has gotten larger. And if we tilted the ramp all the way vertical, that's the component that would survive, which is exactly the experiment we talked about Galileo doing to arrive at his conclusion that objects fall at the same acceleration. When the ramp is raised vertically, what is the net force on the block? It's true that the support force has disappeared, but the net force isn't zero. We know this block will fall, and it will fall freely with no influence from the ramp. The only force acting is gravity, mg. Same story, slightly different picture. That the result, the sum total of all the forces acting on Nelly is the force that's propelling Nelly, accelerating Nelly downhill. Wait, that's the result? Yeah, check it out. If we want to talk about these two forces, the gravity and the normal force, we need a parallelogram. That parallelogram has a diagonal like that, which is the piece that I highlighted a second ago. Absolutely. Now we're ready to talk about Newton's second and third laws of motion. Galileo laid the groundwork, but Isaac Newton had the formal math and a little bit more sort of defining things to put a nice polish on Galileo's work. Newton's sort of addition to this story the motion remains the same unless acted on by non-zero net force. Now, if there is non-zero net force, the motion will change. In other words, acceleration. And the amount of acceleration we get is proportional, according to Newton, to the size of the net force. To increase the magnitude of the acceleration, we push harder. We can affect the force. The acceleration is the result. So we think about independent variables that we can control and those variables that are dependent on them, like the acceleration. The more massive an object is, the harder it is to accelerate, the more we have to push. It's mass that does the job of telling us how much acceleration we get for a given force. If we talk about different objects with different masses and we apply the same force to each one, as the mass increases, this fraction decreases, right? If we increase the denominator from 1/2 to 1/3 to 1/4 to 1/10, the bigger the denominator, the smaller the fraction. So the smaller the acceleration. We say that acceleration is inversely, oppositely proportional. As one increases, the other decreases to mass. Put it all together. There it is. The acceleration produced by net force on an object is directly proportional to the net force, is in the same direction as the net force, which makes sense. I don't want it to move in some other direction that we're not pushing it, and is inversely proportional to the mass of the object. Let's say that in math. There it is. If we double the net force, we double the acceleration. If we double the mass for a given force, the acceleration will be cut in half. An extra factor of 2 in the denominator is like multiplying by an extra half, an extra factor of 1/2. So we end up dividing the acceleration by 2, cutting it in half. From top left to middle left, we double the force, we get twice the acceleration on one block. But if we double the force and double the mass, twice the force on twice the mass gets us the same acceleration back, because If we double the top and the bottom, that's going to divide out to not changing anything. We just multiplied by 1, 2 over 2. From top right, one hand accelerates the brick. If we use the same force, now not two hands, just still one hand, and we have 2 bricks, we get half as much acceleration. If there are 3 bricks instead, we get 1/3 of the acceleration, and so on. Because mass now shows up in one of our formulas, we can't put it off any longer. We have to talk about the difference between mass and weight. Mass is a measurement of how much matter makes up an object, or it's a measure of how much inertia an object has. Weight is traditionally the force exerted. So weight is a force. Mass is not a force. Mass is mass. It's how much matter exists here. Weight is the name that we give to the force of gravity that acts on that much mass. Mass can change independently of gravity. No matter how much gravity is acting, if we increase the mass, we have increased the inertia of that object, and we measure it with kilograms. Weight is the force that acts due to gravity, and the unit for force is newtons, at least in the metric system. In the I guess the American system, it's often pounds, but newtons is what we'll use. And there are few things that annoy me more than when some advertisement, some commercial on TV, and they're advertising some super light vacuum or something, and they pick it up and they say it only weighs 3 kilograms. No, it doesn't. Nothing weighs kilograms. If it weighs, it weighs pounds or newtons or something. It has a mass of kilograms, but those are not the same measurement. Mass is quantity of matter, and it's the same answer whether we are on Earth, on the moon, on Jupiter, at the sun, in deep space. Mass is mass because we're just counting the matter. How much is there? Weight has to do with where we are and what the gravitational forces acting on a particular thing are. If we take a mass to the moon, its weight will change, but its mass will still be its mass. One kilogram, a mass of 1 kilogram, weighs 10 newtons, or 9.8 newtons. We have Newton's second law, that acceleration is equal to net force divided by mass. Now, what if the only net force, what if the only force acting was gravity? So that the net force is equal to the only force, which is the weight. Now, we have already talked about the acceleration that a thing evidences when it is subject only to gravity, it's free fall. And we know the acceleration of an object that's free falling, it's 9.8 meters per second squared. I'm going to call that G, the acceleration due to gravity. That's why G. So if we cross multiply by mass, and the weight is mg, which explains why every time we talked about weight a few slides ago, we used the expression mg, because 1 kilogram times the acceleration due to gravity gets us kilograms times meters per second squared gets us newtons. Here we are, free fall. The greater the mass, the greater the force, because mg. But the force is equal to the mass times the acceleration. So sure, increase the mass, that means gravity's pulling harder, but there's more mass. So it takes more force to accelerate the thing. And those two effects cancel out. And the acceleration of every object acted only on by gravity is the same. And so we see Newton's second law sort of showing up to attach some math to Galileo's experiment, dropping objects off the Leaning Tower of Pisa. Now, Galileo's whole thing was that we had to control for the effects of the air. So Galileo knew this, that if an object actually falling through the air isn't technically freely falling. There is a resistive force, the drag, as a result of the air moving through the air. That resistive force acts opposite the force of gravity. And it's possible that that resistive force, which depends on how fast the thing is going and the size of this frontal surface area, in other words, that's how much area here, how much surface is encountering air as it goes by. This surface here on the top of this sack doesn't really bump into the air, not the same way that the bottom of the bag does. If it's going fast enough that air resistance is equally strong to the force of gravity, then what we've got is an equilibrium situation. If R, the air resistance, and mg are equal, they cancel each other out, and we have no net force. We're back to a zero net force situation, and so we're in equilibrium, and the acceleration becomes zero. The velocity remains constant, and we can call that terminal speed, or terminal velocity is the equilibrium condition for air resistance, when air resistance and gravity are equally strong. As the skydiver's speed increases, air resistance increases in strength up to a point that the air resistance and the skydiver's weight are equal. This same idea has to do with, I mean, there's um, a fair amount of science has been done. Cats always seem, if they fall, to land on their feet. And one of the reasons for that is that they're able to adjust their bodies in flight to maximize air resistance. A cat reaches terminal velocity almost immediately. It's really incredible. That instinct takes over. And if they reach terminal velocity, the sooner they do, the more time they have because they don't speed up anymore. If they continued to speed up, they would reach the ground sooner. But if they can stop speeding up, then they have more time again to rotate so that they land on their feet. A coin and a feather fall at different rates when air is present because the feather very quickly reaches terminal velocity. The air resistance acting on the coin doesn't get to speed up, doesn't get to increase so that the air resistance is equal to the coin's weight because the coin is so much heavier than the feather, which helps explain, I guess, why, Aristotelian thinking says that the coin and the feather are made up of different quantities of earth and air, I suppose. But it's all about mass, and it was Galileo's intuition that it's the air. If we used a solid coin and a hollow coin, we can control for the air. Or if we do this experiment even better, in an evacuated chamber, there's no air resistance, and we can observe the acceleration being equal. Air resistance isn't the only force that can impede motion and slow us down. Well, I got to be careful there. Air resistance can stop us accelerating, but it won't slow us down. Friction can slow us down. We've talked about friction already. Galileo was able to infer that if we could remove the effect of sliding over some rough surface, that these things would slide forever. How strong friction is depends on what kind of surfaces are in contact, and it has to do with the atomic interactions at the surface. We might do an activity in the next couple of classes to get at how strong friction is against, how can we measure that? Right, I forgot. Friction can also put us in equilibrium situations. If we are sliding a refrigerator or some other object across a floor at constant speed, and constant speed, remember, that's one of those phrases. Constant speed means no acceleration, which means if we think about Newton's second law, that's an A, it's trying. A equals, add up all the, let me write it this way. The net force, if the acceleration is 0 because our speed is constant, then in order for the right-hand side to be 0, the mass of the refrigerator isn't 0. And even if it was, we'd be dividing by 0, and that's a problem. So the only way we can get the right-hand side of this equal sign to be 0 is if the net force is also 0. Now, in order for the net force to be 0, Sanjay's push and the resistive force of friction have to be equal and opposite. Don't, it's tempting to pick B, but it's not enough to say equal because forces are vectors. We have to specify direction, equal and opposite. We've talked a little bit about interactions already. The interaction between the coffee mug and the table only happens when they are in contact. And the mug pushes down on the table pushes back up on the mug. And we know that the mug pushes down because if it weren't a mug, if I got up here and stood on this table, it might break. It doesn't break on its own. Things don't just break. They break because something acts on them. And the only thing acting is whatever we set on the table. So if I push on the wall pushes back. This idea of those two objects interacting, the mug and the table, that's the subject of Newton's third law of motion. Whenever one object exerts a force on a second, the second one exerts an equal and opposite force on the first. And it's this idea, like we have this idea, it's kind of gotten everywhere now. It's every action has an equal and opposite reaction. And that's true. But we want to specify, we want to be very clear. If one object exerts a force on a second one, the second one exerts an equal and opposite force back on the first. It's two objects and two objects only. It's not enough just to say, well, equal and opposite. It's what is acting on what. It's two things acting on each other. One force we could call the action force. The other force we would have to call the reaction then, but there's no real rhyme or reason to which one's which. One is the action, the other one's the reaction, or vice versa. That's an exclamation point. Got connected. Here. They're co-equal in this interaction. Neither one exists without the other. They are always equal in magnitude and opposite in direction, and each acts on a different object. That's important. The car tires push against the road, and therefore the road pushes back on the tires. As we press the gas, the tires try to turn, and that rubber tries to push backwards against the road. The reaction to that is the road pushing the tire forward. We do not drive our cars on the road. The road drives us. Responding to our attempt to push on them with tires. Object A The rocket exerts a force on object B. The object A exerts a force on object B. This one pushes the gas out the back. The reaction, we could say, is that the object B, the gas, pushes back with equal and opposite force on object A, the rocket. And this is how rockets are able to achieve thrust. Back when rocket travel was to space was first talked about, some people claimed that it was impossible for a rocket to propel itself in space because there was nothing to push against. You know, if we've got a rocket here on the Earth, you throw fuel out the back and that, okay, we're pushing on the ground and it launches us up. And they didn't realize that it's Newton's third law that allows a rocket to propel itself by expelling fuel. Push the fuel out, the fuel pushes back. It might be tempting to think that if one's pushing on the other and the other's pushing back on the one, that no one will ever get anywhere. But here's the best part. Newton's second law cares about the mass of those two things. It's true that when a cannon is launched out of a cannon, or when a cannonball is launched out of a cannon, the force with which the cannon pushes on the cannonball is equal and opposite, equal to the force that the cannonball exerts back on the cannon. That's true. But because the cannonball has a much smaller mass, it has a much larger acceleration. And that's what the slide is attempting to show with the size of the font here. The F is the same size because it's the same magnitude force, but smaller mass gets us larger acceleration. The larger mass of the cannon gets us the smaller acceleration. That's why, you know, the cannonball is actually able to outdistance the cannon because its mass is different, even though the forces are the same. That means it's important to carefully define the system that you're considering forces acting upon. Unless acted on by net we could add this word, net external force. External to what? External to what? External to the system that we define. Okay, here's an example. Suppose we define the system as just this orange in the cart. And we've got this other object from outside the system exerting a force on the cart. It's true that when the apple exerts a right force on the cart exerts an equal and opposite force on the apple. But if our system of interest is just the cart, if we look at only the cart and the orange in it, there's only one force at work here. There's a force from outside. Somebody came from outside our system and is exerting a force on that system. The reaction force acts on a completely different thing, acts on the apple. So if we ask about the A equals F net over M of this M, the external force applied by the apple from outside the boundaries of our defined system mass M, that's going to produce acceleration. And it's going to look like the cart accelerates. Even though if we consider the larger system, then these two forces are internal to the system and don't, if we watch from outside the system, if all that happens is that my right hand pulls this way and there's an equal and opposite force that way, nothing happens. The only way the system can accelerate is if there's a force that acts externally to it. And we're staring at the picture going, well, I know this is going to work. Where's the external force? It's just like the car tires. The apple's feet, in this case, push on the floor and friction pushes back. That's the external force that creates the acceleration that we know happens. The whole thing starts to move. Why? Because there's a force from outside. So same situation either way. It's just a matter of bookkeeping. Where are the forces and what is external to what mass on which we're interested in collecting the forces to talk about the acceleration. Here's our summary slide of the 3 laws that Newton was able to kind of codify as built on Galileo's work, essentially. And that's the end of this lecture. After you watch this lecture and maybe go back and view some extra pieces of it, there's one large quiz, which is, it's, well, large. It has some questions that are associated with chapter 2, some for chapter 4, and some for chapter 5, so that it's actually it's gonna be the size of 3 chapters. You know what? I don't know why I need to do that. So I'm just thinking out loud here. I'll separate them. Well, I'll do 3 quizzes, one for chapter 2, one for 4, one for 5, but they all are based on this series of, this recording. All right. Thanks, everybody.